People have noticed ever since, well, actually before there were people, that some things can cause other things, or cause them to a certain level, depending on the level of the first thing. So life learned to react to variations in its environment a long time ago. Because some of those variations, such as the scent of a predator, can be indicative of other variations, such as the risk of going out to find food. So, in a sense, relations are a concept that has existed since long before man has had breath. Functions, on the other hand, well, that's a different matter. So a relation is an identified pattern between two variables that may be represented as, well, a variety of things. So it could be a table. So you could have X, Y, Z, A, B, C, whatever. So you could have a bunch of variables all in a table. You could write them as a set of ordered pairs. So say like this. 1, 1. 2, 2, 3, 4, or whatever. If you plot this on a diagram, this would be 3 points. Now, of course, we know that graphs often have lines or curves even. So they are made of, technically speaking, an infinite number of points, even though when you, say, graph it on a graphing calculator, there's a finite number of pixels and thus a finite number of points. Now, if we want to do it by graph, that could be an infinite number of ordered pairs, or ordered triads, if it happens to be a three-dimensional diagram, or even ordered sets in general, because you could have many variables involved. For now, though, we'll mostly deal in 2 dimensions. So we could also deal with an equation. So instead of, oh, see this line on this graph, we have just a mathematical expression that expresses that line or curve. Now, a function is a relation where for every value of the independent variable, so the first values, there is one and only one value for the dependent variable. Now, if we had one that was, 3, 3 or something, this set would be a relation. Right now, it looks like a function. But then again, we don't, say, have an equation or anything. So it could be that our sample might be limited. Now, say we have 50 mice, and we're testing their heart rates in relation to external temperature. That's not going to end up coming out as a function just because you have 50 mice. So at every given independent value, so at every temperature point you measure, you're going to have 50 data points, which means that that would be a relation. But if you drew a line of best fit, or a curve of best fit, that would be a function, because for every temperature, you would predict one value for the expected heart rate of the mice. Of course, there are some hazards with using these equations, such as, well, say you find that as it gets warmer, the mice have faster heartbeats. You can't extrapolate this very well. For example, external temperature is 1,000 degrees Celsius. No. So that implies that for predictions, there's something, there's something that causes the predictions to only hold over certain numbers. Now, these concepts are domain and range. But really, before we get to domain and range, we could first think about how we can connect equations, graphs, and functions. So here we have a table. Here we have a graph. Here we have a function. This here, though, this one, this is not a function for the reason that we will discuss shortly. Now, how do we draw these graphs? Well, what your graphing calculator basically does is that for every horizontal pixel, it finds the values that that pixel is supposed to represent by the given scale. It finds which vertical pixel it should color in, and that's pretty much how your graphing calculator will depict this. How will we do it though? Well, we find a few points because we can't say do increments that are 0.1. That would be too much trouble, too annoying. So we just find, say, -2, -1, 0, 1, and 2. Now, how do we go on from here? We do apply this transformation, so apply this function, and we get 4, 1, 0, 1, and 4. This gives us a set of coordinates. Now, after we get this set of coordinates, we will have to mark them down on our graph paper or whatever you're drawing your diagram on. So it happens to be that on this pre-drawn diagram, it would happen to correspond to these points. Please note that slashes are actually not used because you can't tell where on the slash you're supposed to mark. You're supposed to either use dots or crosses or something. But because this line already exists, marking it down with slashes is just a matter of convenience. So dots would, well, hopefully, understandably, be a little bit hard to see compared to bigger marks. Now, x equals y squared. Well, this is a relation. It's not a function because of a test called the vertical line test, which we'll discuss in more detail shortly. But we see that the independent and dependent variables have flipped in terms of which axis is which. So for y, we could list this as 2, 1, 0, and then negatives, but we usually go from small to large, don't we? So x is y squared, and that means 4, 1, 0, 1, and 4. So the coordinates here would then be 4, -2, and 1, -1. Here, 0, 0, 1, 1, and 4, 2. So on this diagram, these would correspond to here, 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 and here. Now, when we identify if a relation is a function, we can identify this by mental math, or alternatively, we can look at the graph and run a vertical line test. So suppose we draw a vertical line, say here, or along one of these pre-existing grid lines, we would find that this passes the vertical line test in the sense that the vertical line crosses a relation only once. So this then is a function. Now, what about this? Say we put a vertical line somewhere. Does it only have one value that's possible for the relation for any given x coordinate? Yes, and therefore, this is a function. Now, what about this circle here? Well, if we put a vertical line, say here, we clearly have two separate values that are possible. And we can't have that for a function. So this fails the vertical line test. This is non-function. Or not a function, depending on how you prefer writing it. So what about this one here? Well, clearly we can run a vertical line test and it fails to only have one possible y value for every x value. And therefore, this is a non-function of x. Wait a second. Why do we say non-function of x? Well, x here is a function of y, because for every y value, there's only one x value. So if we plot x as a function of y, with y being the independent variable, then this is a function. But if we only consider x as the independent variable, this is not a function. A lot of relations, well, a lot of functions, if you mirror them by flipping the axes, will end up not being functions anymore. But for now, we're supposed to assume that the horizontal axis is always the independent variable we're looking for, and thus run a vertical line test. So technically speaking, for now, we should only focus on this result. Okay, so determining the domain and range of equations. The domain is the set of independent variables that have value for the relation. So in other words, where the relation actually exists, all the independent variables there, the entire range there, although you shouldn't use that word. Why? Because the range is a set of the dependent variables that are possible. So the domain is a set of independent variables that are possible. It is the set of the first coordinate of the ordered pairs. Why is it that we usually give it as a range then? Or a range of values, that is? Because you have infinitely many ordered pairs even over a very short line segment on, say, a graph. Whereas if you give it as a range of values, you cover all your bases. Now, domain and range are written in set notation. So here, let's determine some domains and ranges. Here, what values of x exist in this relation? So where this relation has value, what values of x are there? Domain, the set of x is an element of the real numbers. And that's it. So it's literally x is a real number. So anywhere from negative infinity to positive infinity is fine for this domain. What about the range? The range, well, at positive infinity, this goes to negative infinity. At negative infinity for a domain, so for x, this goes to positive infinity for the y value. And therefore, range is also just y is an element of the real numbers. So, what about this one? Well, we see that for any value of x, this thing has a value of y. Therefore, the domain is, as previously, x is an element of the real numbers. Now, what about the range? We see that at positive or negative infinity for x, the y goes to negative infinity. Okay, where does it go up to, though? It only goes up to including 5. So the range is first of all, you need to state that y is an element of the real numbers, and y is less than or equal to 5. depending on area, you might have to state that it's greater than negative infinity as well. But there some places let you get away with not doing that. So, x squared plus y squared equals 25. Well, this is a circle. Does this relation have any values where the x is greater than 5 or less than negative 5? No. Therefore, domain is x is an element of the real numbers and x is inclusive between negative 5 and 5. Now for the range. Is there any value where you have y greater than 5 or less than negative 5? Clearly not. So the range is y is an element of the real numbers and y is greater than or equal to negative 5 and less than or equal to 5. Now sometimes you look at a relation and it has an asymptote. An asymptote is a line where a curve comes infinitely close, but it never touches. This line can be horizontal, as you see here. It can be vertical, as you also see here, or it can be diagonal with some slope value that depends on the equation. Now, whether or not these asymptotes are horizontal, vertical, or if there are multiple of them, these all depend on the curve's equation. So for this equation, we cannot divide by 0 and get a real value. Therefore, we know that x cannot be equal to 2. So these two are the exact same diagram at different scales, and we see that there is no value of y such that x equals 2. Now, what about an x value that makes y equal to 0? Well, you can't get there. So 3 divided by negative infinity is some infinitesimal negative value. And positive infinity, oh, that's some infinitesimal positive value. So those are not equal to 0, even though it has been mathematically proved that recursive ad infinitum is equal to 1. Now, I know this might sound a little bit weird, but it has been mathematically proved that as 1 minus an infinitesimal amount is 1. So, we don't consider that to be the case here. Now, the domain would be the set where x is an element of the real numbers and x is unequal or not equal to 2. The range is y is an element of the real numbers and y is not equal to 0 because there's no x value that can produce y equals 0. It is an asymptote. Now, sometimes that doesn't actually imply an asymptote. Why? Oh, let's say we have a circle like we had up here. There's no x value that produces y equals 6. Is that an asymptote? No. So, saying that there's no x value that produces a certain y value does not necessarily mean it's an asymptote. It has to approach infinitely close to, but never get there to be an asymptote. Now for y equals 2 to the power of x, we see that for every x value, there exists a y value. That is a real number. So the domain is just x is an element of the real numbers. Now what about the range? The range, well, it goes to infinitesimally above 0. There are no negative values here because, 2 to the any value can't be negative. So, range is equal to well, first of all, we need to state that y is an element of the real numbers and that y is strictly greater than 0. Not greater than or equal to, strictly greater. Alright, sometimes we have examples that are a little bit harder than the typical one you might find in your textbook. And this is one of them. We need to find the domain and range, and it's really easy if we use a graphing calculator. But math contests usually don't let you use graphing calculators, if they let you use calculators at all. So, how can we solve this without a graphing calculator, like without looking at this diagram? Well then, we see that x is smaller than 8 by the denominator. Because, well, we can't divide by 0. That would be square root 0. And then, we're dividing by that. That doesn't work. So we can't divide by 0. We also, for now, cannot take the square root of a negative number because that is what is called an imaginary number. It's not a real number. We don't care about it. So it has to be less than 8. And what else? Well, up here, we're taking the square root of x minus 5. So x must be greater than or equal to 5 by numerator. So we see that x is between 5 and 8, 5 inclusive, 8 not inclusive. What else can we see? Well, we can find the y values by plugging these in. So for x equals 5, we would have y is greater than or equal to 0. And for x approaching 8, it approaches positive infinity because we're dividing by increasingly small numbers, and thus the division result will get increasingly large. I mean, as long as the top doesn't also converge to 0 at 8, which it doesn't. It happens to be converging toward root 3. So, less than positive infinity. Now the domain we should state as x is an element of the real numbers and x is greater than or equal to 5 and less than 8. Now, since we know that this is going to be continuous, i.e. there's nothing in between that interrupts this whole thing, we can state that the range doesn't actually go just completely nuts. we know that the range is going to be from 0 to positive infinity, because just looking at this thing, we see that as we creep x upward from 5, we are going to end up with increasingly positive on top and decreasingly positive on the bottom. What does that do? Oh, we're dividing an ever bigger number by ever smaller numbers. Of course we're going all the way up. We don't make any downturns. That's why we can state right here that this is our range. But of course we need to state it properly, which means set notation. Y is an element of the real numbers such that y is greater than or equal to 0. All right. So here we have another example, example 5. Find the values of x such that square root of x plus 6 is greater than x. This basically asks you to find x plus 6 equals x squared. This can give you, okay, let's just write this out. Minus 6 equals 0, x minus 3, x plus 2 equals 0. So x equals negative 2 or x equals 3. Now, technically speaking, x equals negative 2 is perfectly correct because, well, the square root actually has both a positive root and a negative root. However, for now, our current convention is that the square root represents the positive root. If it has a plus minus in front, on the other hand, that would be something completely different. So, first of all, we know very clearly that if x is less than 0, then we're going to have a positive value bigger than a negative value. I don't think this surprises any of us, yeah? So what about when x is bigger than 0? Well, at x equals 0, we have root 6 bigger than 0. Well, okay, that works. So what we're looking for is the point at which they converge. Then 0. Assured. Now, if x is bigger than 0, we look for a convergence. So of y equals root x plus 6 and y equals x is at x equals 3. So, what are we actually looking for? We're looking for where this relationship is true. That means the equality is not where we're actually going to stop. We're going to stop just before that. So the values of x desired values of x are negative 6 less than or equal to x and strictly less, not less than or equal to, strictly less than 3. Now, in set notation, we would have well, first of all, we of course need to state that x is an element of the real numbers. And then we do this part. Well, there is another way to write this. It is interval notation. Notation. You would write something that looks like this, more or less. X is an element of -6 to 3. Inclusive for the -6 and exclusive for 3. So what would happen if we wanted to write something like, oh, x is bigger than 3? We would write x is an element of 3, so not including 3, to positive infinity. Not including positive infinity because you can't include infinity, or negative infinity for that matter. But if this was, instead of strictly greater than, if it was greater than or equal to, we would have a square bracket in interval notation. So hopefully now we are capable of distinguishing between relations and functions. Relations just relate two variables to one another. Functions only have one dependent variable value for each independent variable value. So now that we hopefully know how to distinguish them, well, that's it for this section, and we'll see each other again then next section.